Ridge regularization, we have a square term multiplied with your learnable parameter lambda, and the idea is to add these terms in order to penalize those terms that are not desirable in training your deep learning model. So here is an example of choosing your right regularization strengths that we can choose. And we have the target is to separate the green and the red areas. For L2 regularization with strengths of 0.01, 0.1 and 1, we can see the different strengths that this is overfitting, this leads to underfitting, where the strength is kept at 1, and this appears to be a suitable representation with some errors, and it can be used to predict the outcome of the unknown samples or unobserved samples. So choosing the regularization strength is also a key here. So what is the next topic? That is dropout. And in a complex neural network, all nodes do not take the same amount of responsibility, and while training, some nodes are correlated. We keep this in mind. Some of the nodes are correlated, they are linked in the network, and if we do not include one node into our training, all those nodes, they will not be fired. And also, all nodes in the network are not equally trained. Some nodes are trained much, but some are not. We studied the vanishing gradient problem, and if your update values are very small, some of the nodes may not be updated at all because it is backpropagation algorithm, and it really minimizes the training of your network with a deep network. So if the output in this example, if the output of the node is bad, the connection weights will decrease, right? So we want a good result and we are avoiding a bad result. If the output of the node becomes to be bad, then the connection weight will be decreased and we will promote those which will give a good output. And if the connection weight goes nearly to 0, the precedent connection weights are hardly trained. So all those nodes that are behind those, for example, this node gives a weight value, some weight value. So it is taking input from all the previous neurons. So if this weight value update is not updated that much, it is assigned a very small value, then in this case, all these nodes that take the input from the previous layer, they will be hardly trained. Network will try to avoid training these links. So how can we reduce the structural complexity? We have seen that the model is really complex, and how can we reduce this complexity? So one way of doing this is to simply remove some nodes, and then we train the simplified network. So if we remove this node, then some of the nodes that are linked to this node, we are randomly selecting some nodes to remove from the network. From each layer, we are adding a dropout value 0.5, for example. We are setting like 50% of the nodes, they will not be considered, they will not be fired. So this is a complex network, and we have transformed that into a relatively simpler structure. That's the target of your dropout. So what we will do is, we do this at every epoch, at every training iteration. At every iteration, what we do is we randomly choose nodes with probability of p. Usually p is 0.5, and then 50% of the nodes will not be considered in each epoch. And then we train the simplified network, and all those nodes that are only connected to those nodes, they are trained. For example, in this epoch, some of the nodes are selected. At the next epoch, different nodes will be selected, not the same ones. So if we have 3 epochs, 3 training iterations, all will have different training for the weights. So all the weights that we have here, they will be updated differently, right? Because they are activated. Some of them are not fired, some nodes are not fired. Because this is a fully connected network, we have 2 nodes in the previous layer, so all of them should have at least 2. So we can see all of them have 2 nodes coming as input. So this is the case of a fully connected network. In the fully connected networks, we can reduce the number of links or trainable weights by using the concept of dropout, and each epoch will have a different number of nodes that are fired. And at the test time, what do we do? But at the testing time, we have the complete model. We are not changing the model. We are not changing this model. We are just training with different dropout nodes. So use all the nodes without dropout. Instead, what we can do is the connection weights is scaled by p. Why? Because at the training time, at this node, it had the probability of p. So it is always present. At test time, we multiply by factor of p. In the training time, we selected p.5, so we have lesser number of nodes, so we multiply this value with the weight values. At the testing time, we use all the nodes without dropout. This is one option. Instead, the connection weight is scaled by p. So this is your net output here in your network. So we have different networks, and what we are doing is we are actually taking the averaging. The concept of averaging is applied. So we have different networks for each epoch, 1, 2, and 3. 3 networks. We have like 3 different versions. So at the end, what we do is we multiply it with a factor of 0.5 and average the net values. This is how we apply the weight values update. So for different neural networks, we are going to multiply it with a factor of p, the link nodes, at the test time. And here is an example. Street view house numbers using the concept of dropout on the convolutional neural network, and all the activation functions they are using is ReLU activations. And different papers, they show their error values, and we can see some of them are using dropout in fully connected layers. So we have error percent of 3.02, and then again dropout in all the layers, we have 2.55 result, and this has the least one too. So different papers, they classify or identify the street view house numbers using convolutional neural networks. And Dropout plays a significant role because it simplifies the network training. And another example on CIFAR dataset, CIFAR 10 and CIFAR 100. Images drawn from 10 and 100 categories, and we can see the best performance with convolutional neural network. With max out, we have this lowest value, and for max pooling with Dropout using 100 categories, we have a performance of 37.2. So what we are trying to prove here, or trying to understand here, that Dropout does play a significant role in reducing the complex network training, complexity in the network training. With a simpler structure, the network is able to learn better. So if we are not doing the Dropout, in that case, all the model will become very complex, and it will trying to learn all the network features, including those that are not required, such as noise in the network. It is also learned by the convolutional neural network or deep neural network, and in some cases it is not desirable. So without Dropout, unit needs to compensate for mistake of other units, and you are updating the weights and using back propagation. So during the back propagation, if some noising is being learned, it also becomes a part of the training, and which is not desirable. This leads to overfitting, since these co-adaptations do not generalize to unseen data. Dropout prevents these co-adaptation by making the presence of other units unreliable. So with no Dropout, you can see the results of MNIST dataset with 1 hidden layer and 256 real units. But in case of Dropout of 0.5, we can say the network is able to learn the important features in the network. So Dropout is a good way of addressing the overfitting problem. So how can we choose, and what is the effect of the Dropout rate in training at the training time for our deep learning training? So let's suppose this is the architecture for MNIST dataset. The Dropout rate P is changed from a very small number to 1 means no Dropout. 0 means, starting from 0, of course, it will not be used. 1 means there is no Dropout. All the nodes are considered. And we are checking the classification error by changing the value of Dropout probabilities. So if the Dropout probability is increased from 0 to 1, and we are checking the test error and the training error. So although the training error, we can see at the training time, although the training error becomes nearly 0, but we can see here at this time, test error, your test error is starting to increase, but your training error is nearly 0. So we realize that we are facing overfitting if we do not use Dropout. And if very low values are considered, we can see we have a high training error for both test and train time, and we are considering the Dropout with high probability. So that is not desirable, and this range seems to be a good option with different confidence intervals that we have here, error margins you can say, or the confidence interval in this graph. So the pattern of your test error, the training error and your test error seem to coincide, and this appears to be a good range for determining your dropout probabilities. High dropout and no dropout are not suitable, and generally we keep the dropout to 0.5 or 0.45. That is a suitable value for experimentation. Another aspect with respect to dropout that we consider is the size of your data set. That is also a very important factor in training your deep learning model. So if we have a larger data set, the more larger data set we have, the better it is. So if we have a large data set in general, we may not need dropout. We may not even need the dropout. So in this example, we are increasing the data size from 10 raised to power 5, nearly a million. And then we can see that very small data size of 10 raised to power 2 dropout does not improve the error rate and even makes it worse. So we can see that without dropout you have the blue line, and without dropout you have the red line, and with the dropout is the blue line. So we can see here the classification error is greater in the case of very small data set. So if we already have very few samples, and then we are dropping out those samples, some of the nodes, and we are not considering. So our model does not have enough samples to train the network, and therefore the performance is way worse than your without dropout concept. And then we start increasing if we have a larger size data, we can see here that at these points now our blue line is going below the red line. That means that is suitable. So with dropout we should have a less classification error. That is desirable. So for larger data set, we can see that the classification error with dropout is less than your without dropout network. We conclude that dropout barely improves the error rate with a very large dataset size. Even that we can say that the data size is big enough so that overfitting is not an issue here. So with this network, we conclude here that we can use dropout to improve the network performance, to make our network less complex. But if we have a larger data set size, then dropout may not be that effective. So we have to consider the data set size and the dropout, both of them at the same time. You have to consider when choosing your technique to improve the performance of your model. So dropout is a very good and fast regularization method. However, it is a little bit slow. It needs 2 to 3 times slower than without dropout. If the amount of data is large or average, then dropout excels. And when the data is big enough, dropout does not help much. So for average size data up to large, we can see that dropout does improves the performance. But if the data is very big enough, then we may not need the help of dropout to improve the performance of your network. Then we can say that the dropout also achieves better performance than other formerly used regularization methods.